So can you help me pass the slides?
Yes, sir.
Thank you. All right, let's continue on the modeling for round rotor generator. And this is the table we showed on at the end of the class on Monday. We utilize this example to change the excitation voltage, which is the internal electromotive force, EMF, by changing the magnitude. You see the power angle, which is the delta between the generator and the infinity bus will change. Current also change, and power factor will change. So if we decrease the voltage from the initial 23.6 kV, until the minimal value, which is the 6.9 kV. So the delta will keep increasing, and the current will first decrease, then increase. And the power factor angle will change from positive to negative, from lagging power factor to a leading power factor. And we mentioned, so at the beginning, the infinity bus, which is external system, behave as a reactive load. So generator will be a reactive source providing Q to the infinity bus. So we'll provide positive Q to the infinity bus. And the second step, so that reactive power output will become 0. So that, which means the power factor is 0. It's unity power factor. So the generator only provides reactive power to support the internal reactance, because this reactance still consumes a little reactive power. And if you further change the decrease excitation voltage, eventually the infinity bus will have voltage higher than the generator. So the reactive power will change the direction. So the infinity bus will provide reactive power to the generator. So generator will behave as a reactive load. So the excitation voltage keep decreasing from initial value to the minimal value, which is the stability limit. But the current first decrease, then increase. So there could be a relationship for the how the armature current change versus the field current. So this is called the V-shape function, V curve. So there's an example on the textbook, 3.3. We utilize the same generator to start to try to draw how the field current, how the armature current change with field current. So here we assume the excitation voltage E is proportional to the field current. So field current is actually the DC current on the rotor. So that value multiplied by 2000 will give you a good estimate for the excitation voltage. So we utilize the same example. We vary the field excitation such that the generator will change the power factor from a 0.4 leading power factor to 0.4 lagging power factor. And then we calculate the armature current, then we draw the curve. So armature current will be the IT power divided by 3, because it's a 3-phase generator, and voltage, magnitude, RMS value, and power factor. So here we want to maintain the IT power at 14 megawatt. So you see this armature current will be a function of power factor angle theta. So only variable will be theta. So if we know the theta, we'll be able to calculate the field, the armature current. So the theta will be changing depending on those power factor. And the field current is simply just proportional to the field voltage, excitation voltage. Excitation voltage based on the equivalent circuit will depend on this one. So we don't change the outside of system. So the infinity bus will have the same voltage, 30 kV, which is line-to-line voltage, and reactance doesn't change, right? So only the armature current will be variable, also the theta, the power factor. So next, we want to change the theta such that the Paul factor will change from 0.4 leading to 0.4 lagging, which means the angle will change from negative 66.4 degree to a positive 66.4 degree. So we just plug in those angles. So you just determine the interval or step to increase the angle from negative to positive, and you give those value to the first equation. So that will tell you the armature current for each angle. Then you give that current to the second equation, also providing the angle. So you will get the value for the field current. Then you'll be able to draw this curve. Okay. Yeah, so this is just to give you an idea on how the field current change with the armature current, or armature current change with field current. All right, so next we want to move to the Salient pole rotor generator. Before we talk about the Salient pole rotor generator, let's just go back to a round rotor generator temporarily. Let's just go back to this slide. Okay, so for round rotor generator, although the rotor has the D axis and the Q axis, D means the N direction, and Q is a 90 degree leading the direction of N, which is the flux direction. But when the rotor revolves inside of stator, if you are able to see it on the stator, looking at the rotor, there's really no difference because air gap everywhere is the same. Okay, so by using these slides, we spend a lot of effort trying to explain the relationship between several features, right? We start from the magnetomotive force, FR. This is due to the field winding current. And we explain, so this field winding current will generate magnetic field, no matter the generator is operating or not. Even the generator is opening the circuit. As long as you have the field current is revolving inside, you still generate this magnetomotive force. So this one is simply equal to the current of the field current multiplied by number of turns. FR is simply just the current, the field current, which is on the rotor. The magnitude of current multiplied by the number of how many turns you have on the wire. So this can be a constant. And this one will generate magnetic field. And the magnetic field will revolve inside of generator. And that magnetic field will induce this voltage, E, which is excitation voltage. And this is lagging this one by 90 degrees because of the Faraday's law. So to calculate the induced voltage, you need to get the function of this one, then you calculate the derivative, right? And add a negative sign. So that will give you direction of this E. And so we use this slide to try to explain the direction between the phase of FR and the phase of E, but we didn't go into details on how this one change with that one. Right? We use the example 3.3 we just talked about a few minutes ago, but that is for round rotor generator. Let's assume this one is constant and this voltage is also constant. But for Salient pole rotor generator, that can be tricky. Why? Because the shape of the rotor will be different. So the voltage is induced not directly by the magnetomotive force. It's induced by magnetic flux. So you have to let this magnetomotive force to generate flux, which is this. And the flux multiplied by the number of turns will give you the flux linkage connected with the stator winding. Then that one will induce voltage. But the flux depends on the material inside of this magnetic field. So if the inside of the stator is a fully magnetic material, the flux can be really large. But if the magnetic, because if the material is not magnetic, the flux can be smaller. Okay, so which means the flux in the air gap and the inside of a rotor can be very different. And for this case, it's simpler because the rotor has round shape. When it's revolved, it doesn't even the spatial position of rotor relative stator is changing, but the magnetic field doesn't, the flux density doesn't change too much. But for salient pole rotor generator, that can be different, because you can think about in the quadrature direction, there will be more air gap. So the more air gap, which means it's harder to build out the flux. So if we're familiar with usually this formula, in the electric circuit, we know the voltage is equal to current multiplied by resistance, right? So if you have a higher resistance, the current will be smaller. So analogy in the magnetic field will be the magnetomotive force, which is similar to voltage, electric voltage, which is equal to flux multiplied by also R. The R usually we use subscript M to be distinguished from electric R. We call the Rm as reluctance. So if the reluctance is bigger, and the phi will be smaller for the same magnetomotive force. So if you have a fully magnetic material, the R can be small, and phi can be big. But if for the air gap, now the magnetic material Rm can be big and phi will be small. So which means for salient pole rotor generator, when it's revolved, so the winding A will be either facing, sometime will face the poles, either NOS, so the air gap will be smallest. But for the quadrature direction, it will have largest air gap. So which means the Rm here is also is periodical changing relative to the position of the rotor. So we have to discuss that for salient pole rotor generator. So we start from here. So if the rotor is revolving, we won't be able to have a constant readance here, because this readance depends on the indulgence, indulgence of the armature winding, and that indulgence depends on the flux. If the flux is changing, this readance will also change. Okay, so this is the formula we proved for the round rotor generator, which only have like constant X. We call it a synchronous readance. So I have a two component. One is a leakage readance, the other is armature readance. So leakage readance is just model. It depends on the flux in the air gap, and armature depend on the flux inside of rotor. For round rotor generator, the armature will be constant, so both will be constant. But for salient pole rotor generator, both may not be constant. Okay, so how do we model them in for a salient pole rotor generator? We can model the equivalent readance in two directions. One is in D axis, the other is in Q axis. So when the rotor is revolving, and if we stay on the winding A, sometimes we'll be seeing the largest air gap. Sometimes we'll see the smallest air gap. The largest air gap happens when the winding A is in parallel with D axis. But at this moment, the winding A axis is in parallel with the Q axis, so the air gap will become largest. So we can model the readance in two directions. So there's no constant readance or singular readance that is independent of a rotor position. We have to consider the at least two positions of rotor. So we need to define separate readance. Readance is SD or SQ. SD usually is bigger than SQ because SD has smaller air gap in the D axis, and QS has bigger air gap. The bigger air gap means smaller indulgence and smaller readance. So for voltage, we will assume there are two components. Because voltage is a phasor, we can just project the voltage phasor into a D axis and Q axis to get two components. We can also do similar things for armature current, for to get the D component and Q component. All right, so next we, this one basically just V, right, from the original formula, and this one is just I from original formula. So third component, because there's no constant singular readiness, we just assume there are two constant readinesses. One is SD. That one need to be multiplied by the current in the same axis, and also SQ is another constant component in the Q axis multiplied by the Q axis component of current. So this will be our new formula. We won't be able to draw such a single circuit because there's no, if you draw a single circuit, and this readiness will not be constant. It can be changed with the time or angle of the rotor. All right, let's consider a simple case, and we still want to derive some formula to calculate, for instance, the power, IT power of the generator. And then we can compare the formula to the formula for round rotor generator. And we can also discuss on how good the approximation can be if we just ignore the saliency. We use a round rotor generator anyway. Yeah, so we can utilize this example. So this is the equivalent circuit, not equivalent circuit, but it's the equation. And we can split the equation depending on the color. I use the magenta color to indicate the D axis, blue color indicate the Q axis. So let's just split the one equation into two separate equations for two axes. First of all, the E is Q, right? E is always Q because if we define based on our initial time, so the phasor E of the winding A lie in the Q axis because the voltage reaches maximum value when the winding A axis aligned with Q. So we have explained this one for round rotor generator. So it's the same for Salient pole rotor generator. So E will be in the first equation, and then this negative VQ will move here. So this item, so ID is in D axis, but because it's multiplied by a purely imaginary number, it becomes a Q axis component, so it has to move here. Similarly, this one will move to the second equation in D axis, and together with just the VD only. So we have two equations, and we need to draw the phasor diagram using those two equations, and also we also want to have the single phasor diagram of the original one equation. So which will be this one. So here we use E. So X here is Q axis. We use E as a reference. And we assume the generator is delivering IT power, such as the voltage of the infinity bus is lagging the E with delta angle. And for the voltage, we can split into two components, the one component in Q and the other component in D. So which means we can use this rectangle to determine the D and Q axis. We also assume the current is lagging voltage by theta. So here we just draw the lagging power factor phasor diagram. You can easily draw another case for the leading power factor case. So which means IA will be leading V. So for the lagging power factors, IA will have D component and also the Q component. All right. So first, the voltage will have, so the current will have the voltage drop on the in the Q axis, so which is this item. That is equal to the D axis component of current multiplied by the readiness in the D axis. And because this readiness is a purely imaginary number, so that will generate the voltage drop in the Q axis in parallel with X. then another voltage drop in the D axis. So that will finish this phasor diagram, right? Does it make sense? Everybody follow? Okay. Next, we can get the magnitude of each side of the equation. And from the first equation in the Q axis, we have the RMS value E, subtract basically the magnitude of the Q component of V. And the right-hand side, we just get rid of that imaginary unit. So this equation tells, so this RMS value of E is subtract the voltage multiplied by cosine delta, which is actually exactly just a VQ. And the remaining part will be this voltage drop, which is equal to this component. That's what this first equation tells. Okay. And the second, from a DS equation, we can get a similar we can get a similar equation. The left-hand side will be the voltage phasor multiplied by sine delta, which is actually exactly the D component. And this one is equal to the voltage drop here. It's just a translation of the original equation in D and Q axis separately. Okay, from first equation, we can get a formula to calculate ID. And the second equation, we can get a formula to calculate IQ. And now we are ready to derive the accurate formula for Salient rotor generator to calculate the power output. So we still start from this form. This is still correct. So it's 3 times RMS value of the voltage times RMS value of armature current, then power factor angle, power factor. We have to determine this item using the phasor diagram. So this is equal to the RMS value of armature current multiplied by power factor angle. So if we try to find out this is the current, right? And multiplied by cosine theta, this is theta. So this item is actually equal to this length if we utilize that triangle. Okay, on the figure is equal to 2 segments. One is A to B, the other is the D to E. So what is A to B? A to B, we can utilize the lines of IQ. Multiply this one by cosine delta. We utilize this triangle, this angle delta. And what is the D to E? D to E, we can utilize this triangle because we know this line is ID. Then we multiply this one by sine delta. Okay. So we'll get this second expression. So from here, we can just plug in the ID and AQ. And you only just need to do a little simplification. You can easily get this accurate formula to calculate active power, the 3-phase active power for a Salient rotor generator. So the difference compare with the round rotor generator is only the second item. The first item is exactly the same, but you need to utilize the XD instead of XQ. So if we ignore the second item, so this one will be similar to what we have, right? Compared to the round rotor generator, the same formula, but here we call it a singular readiness. So this is the round rotor generator. We replace the single reactance by ISD to ISD. And definitely there will be a second atom, but second atom can be very small if the XD and XQ are very close. So we can ignore the second atom, and we can use this one to approximately calculate the IT power. Okay, so how good is this approximation? So we can show this table for typical values of XD and XQ. So here all the values in per unit. We'll explain what per unit mean later, but it basically just means you define the basis and divide the actual value readings in ohm by the basis, such as you generate some value like a fraction or percentage. You can compare. So you see for thermal unit. So thermal unit, round rotor or cylindrical rotor generator? Which one? Do you remember thermal units? Are they round rotor or cylindrical rotors? Yeah, this is gas turbine generator, but but the thermal unit or steam turbine generator will be similar. So it's a round rotor, and only hydro unit a cylindrical rotor generator, because the thermal unit can operate at a very high speed. It doesn't need so many poles. It only needs 2 or 4 poles, so it can operate at a high speed. But hydro unit cannot operate at high speed, so they need many poles. So it will be a cylindrical rotor generator. So come back to this slide. So thermal unit, you see the SD, SQ fall into the same range, so they can be very close. This is the readings due to the air gap. So usually it's only less than 10%, and resistance can be very small. Usually can be ignored for approximate calculation. And for hydraulic unit, hydro power plant generator, you see the SD, SQ, SD is slightly bigger than SQ. So difference not big. Difference like maybe 30%, 30 to 50%. And the percentage of the leakage readings to the either D or Q readings can be bigger compared to a thermal unit. Okay, so if this difference is not important to calculation, you can utilize this approximate formula. Otherwise, you can utilize the accurate formula. All right, so we'll continue to talk about the transformer. So we finished the modeling of generator. For transformers, transformers have 2 legs. On each leg, you have winding. So you can call maybe one side to be a primary winding, the other side to be a secondary winding. Because usually you assume the primary winding will be connected to source, and secondary winding will be connected to a load. Okay, but definitely you can call either way to be a primary. So if the primary side has more wears, more turns than the secondary side, you can see the density on the left is much bigger than the right. So you can imagine this is like step down transformer, which means voltage will decrease from the primary side to the secondary side. Definitely, you can also have step up transformer. Like if you have a generator which generates electricity at, for instance, maybe 30 kV, not very high, but when it's connected to the transmission grid, you need to utilize a step up transformer to increase voltage to a very high voltage, like 200, 345, 500 kV. So then you will need a step up transformer. So we have a number of things to model if the transformer is not ideal. If the transformer is ideal transformer, So we know the ratio of the primary side voltage to the secondary side voltage basically equal to the ratio of the number of turns. So that's very simple. But if it's not ideal transformer, we need to model many things, such as the leakage of the flux, because there could be some flux not staying inside of this core, so it can leave from transformer. So we also need to model that one, and also the wear may have some resistance, so that can generate some power loss, and there could be some eddy current because of change of the electromagnetic field, and so the eddy current will generate some heat, and that also need to be modeled. Okay. So before move on, and this is the equation we talk about. That's an analogy to the equation in electric circuit for voltage equal to current multiplied by resistance. But here, the magnetomotive force, which is the current to build up the magnetic field, and which is equal to the flux multiplied by the reluctance. So 1 over reluctance, usually also called the permeance. So this is an analogy between the magnetic circuit and the electric circuit. So for ideal transformer, we ignore the winding resistance, so there's no leakage flux. The permeability of the core to build up the magnetic field is 0. So which means you don't need much flux. You only just need to build up the flux for the transformer. You only need 0 magnetizing current. So which means for the primary side, you connect that to a source to give it a little current. Even the current is very small, that can build up the magnetic field, which is sufficient to let the transformer operate. But in real transformer, you may need to add some minimal current. And also the core loss, there's no eddy loss with ideal transformer. But for real transformer, you need to model everything. So how to model a real transformer? We start from ideal transformer. So this is the principle we know, right? So the ratio of voltage is equal to the ratio of a number of turns, which is defined to be A means just N1 divided by N2. Because of the power balance or energy conservation of energy, so E1 by E2 is equal to I2 by, oh, this is, I think this is, oh yeah, this I2 prime is defined to be the primary side current. I will explain on this circuit, yes. Okay. So in the box, there's an ideal transformer. Then we connect this ideal transformer to the auxiliary circuit on each side. Okay. On the source side, we have a source voltage, and we have these 2 branches to model the magnetizing current and also the eddy loss. And on each side, we have an impedance to model the resistance of the windings and also the leakage reactance, leakage flux. And this is the load connected to the transformer. So the center side, we have a current leaving the ideal transformer, which is I2. And the current going into the ideal transformer is I2 prime. Why I use is I2 prime? Because later we're going to get rid of this ideal transformer. We will move everything to one side. So let's go through the auxiliary circuits we added to this ideal transformer. First, we add S1, S2. they are modeling the flux leakages on both windings, primary and the secondary side. R1 and R2 is just the winding resistance. And next, we need to model the current under no load condition due to finite core permeability and the core losses. So we use a shunt branch. So it will be a reactance in parallel with the resistance. So that will need a minimal current to build out the magnetic field. And that also need to balance the loss of due to the eddy current. So the IM is a magnetizing current to set up the core flux in phase with the flux and lagging the primary voltage by 90 degree, because IM is equal to the primary side voltage divided by the reactance, this shunt branch. IC is actually the eddy current. And it just provide the electricity to balance the loss of the transformer to build up the magnetic field. So when the low side, the secondary side is open the circuit, so which means the current going to the ideal transformer is 0. So all the current from the source will go into those two branches. So you can utilize this one to measure the current going to those two shunt branches. So that is related to there's an open circuit test or short circuit test to estimate the perimeter. So when you do the open circuit test, you just need to open the secondary side, the winding, and then the circuit. Then you add very little voltage and to calculate the power loss. Okay, then power loss will basically determine, you can calculate how much resistance is. Then you can calculate the current. So I assume you have learned how to do the short circuit, open circuit test in the 325. For short circuit test, you mainly calculate the impedance of the series due to the winding. Okay, so our goal is to have single equivalent circuit, and we want to get rid of this ideal transformer, so we can utilize this circuit in the power system model. So one thing we can do is we can move this series branch in the secondary side to the primary side. So to do that, we just need to utilize some transformation based on this ideal transformer. So for any current on the secondary side, if we move that current, let's see, there's I2, we want to move to the left-hand side, become I2 prime. So that current need to be divided by the ratio. For any voltage, you want to move, if there's a V2, you want to move to the primary side, that voltage need to be multiplied by ratio, and the impedance need to be multiplied by the ratio squared. So you can generate this circuit. You basically simply just move every component to keep the topology, the structure, and put them on the left-hand side of the ideal transformer. And for the values, for the impedance, current, the voltage, you just utilize this transformation to get their transform value. Then you can, so then the ideal transformer on the right-hand side become opening the circuit, so you can get rid of this ideal transformer. So you get a single circuit representing the both windings of the transformer. Definitely, you can also transfer everything to the left-hand side. If you do the transfer to the, you can also transform the primary side current voltage impedance to the right-hand side. If you do that, current need to multiply by ratio, voltage divided by ratio, and impedance divided by ratio square. So either way is good. Okay, so is this clear? Yeah, I assume everybody already learned this one in 325. Okay, so what is important to us is to get some approximate equivalent circuit, which is good enough for calculation for power system, right? Because our goal is to study the power flow and also the operations and for the power system. So transformer, we want to get just accurate enough equivalent circuit, which is convenient to use. This equivalent circuit is accurate, but it's not very convenient because the topology is too complex. We have this shunt branch and also we have a 2 series branch. So that those are not convenient for calculation. So we want to get some approximate circuit. We will take 2 steps. We use this as one example. We transfer everything to the primary side. Then we'll take 2 steps to get a simpler circuit. Definitely, you can transfer everything to the secondary side to take a similar 2 steps. So let's use this one as an example. Okay, so because the source voltage and is very close to the voltage on the ideal transformer. So basically, the voltage along this from the left to the right will be very, very similar because the current going to those 2 shunt branches are very small. It's very small. So which means we can merge the 2 series impedance into one. And we can call the total impedance as ZE1. Okay. So what we need to do is just move this shunt branch to the left to be connected to the source directly, such as the 2 series branch can be added. We can calculate the total. That gives you the total equivalent impedance. So we'll get this circuit. So on this circuit, everything is transformed from the secondary winding. So if for any component, because this Z represent total impedance, it's a sum of the impedance from the primary side and another from the secondary side. For primary side, that will be the same. That's the original value. For the secondary side, that has to be transformed using this transformation. Okay. By using this, based on this circuit, we can know we can have those 3 equations. First equation just based on the Kirchhoff voltage law. Second equation just calculate total resistance. So R1 is from the primary side, doesn't need transformation. R2 is from the secondary side. It need to be transformed. We need to multiply this one by A squared. And this one will be the total resistance. Similarly, for reactance, they have 1 component from primary, second from the secondary. So this will be the total reactance. So by doing this, we make a topology simpler than the accurate circuit. You can do similar things. If you transfer everything to the secondary side, you generate the same topology. But the value in the impedance, the secondary there will be a 2 component similar to those formula, but primary side you need to transform, and secondary side you don't need to transform. So for instance, the resistance secondary side will be the same, will be original value, and primary side resistance need to be transformed by dividing that value by the ratio square. Okay, so this is step number 1. We simplify topology. Step number 2, if the transformer designed with a very high permeability core and a very small core loss, which means let's just assume the transformer design well good enough. So we can just simply get rid of that shunt branch. Okay, So by doing those two steps, we generate just a single impedance to model the transformer. Okay. So next question we need to answer is whether you want to transfer everything to the primary or secondary, because if we transfer everything to the primary, all the calculations based on the primary side voltage. The thing about the primary side can be a 220 kV, and the secondary side could be maybe 35 kV or lower voltage. So if we do everything on the primary side, all the calculation is about the 220 kV. But if we take the second, all the calculation based on the lower voltage. So they will generate answer differently. But later, once we introduce the per unit system, they will generate exactly the same value, because by checking those three equations, we just compare the two group. They may have different unit, but the relative value are same. So if you define a base value, for instance, for the primary side, you define the 220 kV as the base value. Any voltage will going to divide the voltage by the base value. You will get percentage of operation. Similarly, for the secondary winding, you have maybe 35 kV. You also use that as base value. The percentage wise will be same. Okay, so that will be addressed by the per unit system. Let's continue on Friday.